Hello and welcome to the lecture series on power electronics. We were discussing the recent trends in power electronics, and in the previous lecture I talked about cascaded multi-level inverter and some of the features and the operation of a cascaded edge bridge multi-level inverter. I also told that basically there are two more classical topologies which are often used in multi-level inverter application, and they are the diode clamped inverter, and the third one is the flying capacitor converter, flying capacitor multi-level inverter. But although they had been they do find application in industries, all of these converters, especially the diode clamped has been quite popular with the in industrial application. But all these three classical multi-level inverter topologies actually suffer from some drawbacks. There are certain shortcomings. So let us discuss that, and then I would come to I would be talking about a new type of multi-level inverter which actually takes care of the shortcomings that are actually associated with the conventional converters. Okay, so let's start. So you could see here I have drawn a table which actually shows the various parameters for the three types of multi-level inverter. DC here stands for diode clamped, FC is flying capacitor, and CHB is the cascaded edge bridge multi-level inverter. So let us try to see how they perform on certain parameters. So let's take the first parameter be the switch count, the number of switches required to generate multi-level output. So this formula twice of n minus 1, and which is common in all the three types of converter, it is basically the number of switches, the IGBTs or the MOSFETs that are required to generate n levels in the output voltage waveform. So basically this n refers to the number of levels. So for example, if one is interested in generating say 7 levels in the output, then we require 7 minus 1, that is 6, times 2, 12 switches. Similarly, as we increase the number of levels, the number of switch count is going to increase considerably. Now take the second parameter, which is the DC source requirement. So DC source in a diode clamped multi-level inverter is only one. In flying capacitor also we require only a single DC power supply, but in cascaded edge bridge we require n minus 1 by 2 DC sources, where n is again the number of levels. So if I am interested in generating 7 levels, so 7 minus 1 is 6, by 2 is 3. So 3 DC supply or DC source is required to generate 7 level output. And here I am actually talking about the symmetric configuration of CHB. And you see, if I increase the number of levels, so the number of DC supply increases considerably. Then the third parameter is the number of diodes required. So although the diode clamped multi-level inverter required only a single DC source, but number of diodes required is very large. So n minus 1 into n minus 2, a quadratic function of n. Okay, while there is no requirement of diode in flying capacitor and cascaded edge bridge multi-level inverter. Talking about the number of capacitors, so this is basically the inherent disadvantage which is associated with the diode clamped and the flying capacitor. In diode clamped, number of capacitor requirement is n minus 1 for n level generation, and flying capacitor is quite large. For flying capacitor it is n into n minus 1 by 2, again a quadratic function of n. while there is no requirement of capacitor in cascaded edge bridge multi-level inverter. So you could see there are certain advantages and certain disadvantages associated with all the three conventional topologies. Okay. So let me put it in this was in tabulated form. Let us now discuss in some actual terms. So let's take this switch count. So large switch requirement for higher levels. In all the three types of multi-level inverter, we require large number of switches. Okay, for large for many levels, n is large. If n is large, moreover, large battery or DC source requirement for higher levels. So what is the disadvantage associated with these two? The disadvantage is in the cost. This has to be at higher cost. So as the number of switches increases, number of DC supply, especially the DC supply. If DC power, it's quite costly. Say we are operating using a battery, so battery is quite costly. Okay. Moreover, it requires maintenance. And the third thing, it has got life period of say 4 years or 5 years. It has to be replaced. If we are talking about lead acid, so although some other good batteries may have larger time of replacement, but still they need replacement, and they are quite costly. Okay. Moreover, if one more thing, if the number of switch count is more, large number of switches are there, then again there is a problem of losses. So more the number of switches, more will be the losses. Okay. How? Because you see that two types of losses are associated with a switch, which is one is the conduction loss and the other one is the switching loss. Okay. So more the number of switches, definitely these two losses are going to be more. So you just have to multiply the loss in one switch to the number of switches used in some of the configuration, but definitely it is not a simple mathematics, because for calculation of the number of levels, talking about the number of levels, the voltage stress across the switch would be varying. At different switches it will be different. So definitely the loss associated with the different switches will not be same. It won't be uniform. It would be varying. Okay. But one thing is clear, that more the number of switches, more will be the losses. Okay. So then the another point is higher voltage stress. So this is a issue which is associated with conventional multi-level inverters, that the voltage stress across the switch is quite high. So if that is the case, then what happens? If voltage stress is high, then blocking voltage is higher, but still small amount of current do flow, we know that. So loss during conduction is the product of the blocking voltage and the current which is flowing through the switch. So if higher blocking voltage, so again the loss, the conduction loss increases, and moreover the switching loss will also increase. Okay. Anyway, now the total standing voltage. The total standing voltage basically refers to sum of all the stresses, sum of all the maximum stresses that occur in all the switches in a converter or inverter. Okay. So this basically refers to or this basically indicates the actual ratings of the various switches that are required for a particular topology. Okay. So higher this value, higher would be the rating of various switches, and consequently higher would be the cost of the converter. Okay. Then one more important thing is the voltage, the capacitor voltage balancing issue. You see, although there is no capacitor in CHB, but we do have large number of capacitors in diode clamped and flying, especially in flying capacitor, n into n minus 1, a quadratic function of n. So large number of capacitors are there. So capacitor needs charging, and in the entire process of operation it do gets discharged also. Okay. So charging and discharging process has to be monitored, okay, so that the voltage across the capacitor remains constant, fixed, so that a stable output voltage, multi-level output voltage is generated. So here comes the issue of actually sensing the voltage that is appearing across the capacitor and trying to maintain it to a particular level, okay. So we need to adopt some modulation strategy and incorporate that voltage balancing problem into the code that basically is used to control the output voltage, and that basically creates some issues, okay. So we do have problem with capacitor voltage balancing in diode clamped and flying capacitor multi-level inverter, especially when the diodes number of capacitors are quite large, okay. And then complex circuitry. Complex circuitry, if we have more number of switches, and then definitely controlling them requires a complex circuitry, a system of drivers, okay. And then again we do have to, since we have to control the capacitor voltage also, we have to maintain it at a particular level, then there also we need sensors, okay. So this actually adds up to the complexity of the circuit. So these are the various issues that are associated with the conventional multi-level inverters, that is the diode clamped, flying capacitor, and the cascaded edge bridge multi-level inverter. So now we will look into what we can do with this. So actually more recently newer topologies have been proposed in this area of multi-level inverters, and we will see that they are quite they have got lots of advantages compared to these conventional topologies, and they do overcome the shortcomings that are associated with conventional topologies. So we would be looking into the working of one of the topology, which is called the packed U-cell multi-level inverter, and we would look into its operation, and we will also see how it has got inherent advantages associated with it compared to the conventional topologies, okay. Thank you, and I hope you liked the lecture.